Welcome back for Unit 2, Lesson 2. We're continuing our study of geometry, the fundamental building blocks of geometry. I want to take you through a little bit of a mental exercise, if you will. Imagine you're learning a new language, right? And you're learning a new language, but the only tool you have to learn the new language is a dictionary in that language. Maybe it's Urdu, or maybe it's Spanish or French, but you don't know any words, not a single word in that language. All right? So you might be tempted to look up, let's say the language is English, and you're going to define the word run. So you look up the word run. You at least know the alphabet, but you don't know what the word run means. And run, and you look it up in the dictionary, and it says something like to move oneself at a rapid pace. Right? No, now you got a problem. You don't know any of those words that define that word, so you might be tempted to look up all of those words as well. And you can continue this on and look up all those words. What does the word rapid mean? Rapid means quickly. What does quickly mean? Quickly means to move at a rapid pace. And you'll quickly find that you're going in a loop, a circular loop that just never ends. It is impossible to have a system of logic or a system of definitions that does not have some basic terms that are undefined. And that's the point I'm getting to. In geometry, we have undefined notions and we have undefined terms. And in geometry, the undefined notions that we're going to talk about are four. We're going to talk about the undefined notion of point, of line, of distance along a line, and distance on an arc. Okay, so let's talk about those here. So the first undefined notion that we have to kind of build by experience, by drawing, by diagrams, is this concept of points. I've already mentioned it yesterday, right? A point is a locus in space. It has no thickness, no depth, no width, no height. So we don't define it in terms of other things, but other things are determined by point. We have this notion of point, and we can label points with capital letters. I'm going to label this point P with a capital P. All right? And so we can define point. Then we can define line. A line, it is this idea of a continuous set of points, a collection of points that continue in a given direction, in both directions, in two directions, forever, right? And so a line is an undefined point. It can be thought of as all the points going one way and the points going the other. It's a collection of points or locuses in space all lined up, right? And this is line. Notice I draw my line with arrows. Once again, just like point has no width, no depth, no height, no dimensions. It is a dimensionless object. Line has only one dimension. It travels in a single direction, either forward or backward, of course, but along that single direction. But it has no end, and so we typically draw its representation with arrows. So that's a line. And then we want to talk about the concept of distance along a line. So if I define 2 points, I'm going to define another point. Let's call this point A, right? We can talk about distance between point P and A, or distance along a line. And this brings up the use of something called a ruler. Now you notice my ruler has centimeters, so I might be tempted to read this as 3.68 centimeters, right? But it's also, it could be 1 and, let's see, 1 1/4, 1 3/8, 1 7/16 of an inch, right? And so we can have all these different measuring ideas, measuring units, so to speak, measuring systems. But we can talk about the distance between points, and that's an undefined notion or an undefined concept. We can also talk about distance along a circular arc. So let me draw a circular arc with point P at its center, right? I can draw a circular arc. How do I define the distance along that arc from the point B to C? Right? From B to C. Well, I might picture in my mind taking a piece of string and running it along there and then stretching it out and holding it up against my ruler, right? We can talk about arc length in that way. The distance between 2 points on an arc. And so those are our four undefined notions or concepts. Point, line, distance along a line, and distance along a circular arc. Okay? That said, there are some things we can define based on those undefined notions. Okay, we can define angle, right? Yes, angle. An angle can be thought of as a point with a line extending in one direction that we happen to call a ray, right? So this is a ray. And then an angle can be thought of as two rays with a common starting point. Right? And notice I'm defining angle in terms of my undefined notions, point and line, right? A ray is a line that extends only in one direction, and an angle is a combination of two rays with a common starting point. And the common starting point we happen to call a vertex. We can talk about segment. A segment is 2 points and all the points between those 2 points. Or we can talk about it in terms of a piece of a line. It's a piece of a line between 2 points, A and B. Okay, A and B. So that's a line segment. A line segment has endpoints. We can talk about circle. A circle can be thought of as all the points, a set distance from a single point on a plane. Right? So all these points that I'm drawing are an equal distance. Oops, and my pencil lead shifted on me a little bit. So I messed up my circle a bit. Got to tighten that down. That's another problem with compasses here. But a circle can be thought of as all points equidistant. If I use my ruler, maybe centimeters here, if I measure the radius from here, about 3.4 centimeters, it's the same as from here, about 3.4, well, 3.1. Yeah, my compass moved here. But the radius should be the same, about 3.1 centimeters all the way around. Okay? And that's a circle. Then we can talk about arc. An arc is a piece of a circle between 2 points. Let's call this E and F. Points E and F bound a circle, and so this can be considered an arc. An arc is like a circular analogy to a line segment. Parallel lines are an interesting concept. How do we define parallel lines? Parallel, lines that never intersect, right? Lines that never intersect. They go forever in both directions, but they never intersect. So this line is parallel to this line, provided that if I continue forever in the direction to the right, and I continue forever in the direction to the left, they never intersect. Let's define this as line L and line M. Okay? So lines L and M are parallel. We symbolize that L is parallel to M. Okay? L is, and I just wrote that backwards, didn't I? L is parallel to M. It's fun writing upside down. L is parallel to M. There we go, writing upside down. All right, and you'll notice they say the same distance apart. Now, distance between a line is difficult to define, but that's about 3.9 centimeters, and that's about 3.6 centimeters. So it's I didn't draw these truly parallel. But if they were parallel, I would find that the distance between them stays constant, right? Parallel lines. Lines, perpendicular lines. Perpendicular is kind of tricky to define. Two lines are said to be perpendicular if the angles formed by them are the same. That is to say, I'm going to draw a line, okay, and I'm going to label this line L, okay, and I'm going to put a point on a line, and I'm going to use my compass to make this construction. You're going to learn this construction later, but I'm going to draw this construction very precisely here. So I'm going to measure to one side, turn around and measure to the other side. I'm going to open my compass a little wider. I'm going to draw a circular arc up here. I'm going to draw a circular arc down here. And I'm going to draw a line through the two intersection points. We're going to label this line M. So we would say L is perpendicular to M. That's the symbol for perpendicular, kind of like an upside down capital T. And it's perpendicular because this angle right here is exactly the same as this angle right here. Now, if we talk about measuring of angles, you may recognize this as a 90 degree angle. 90 degree angle in both cases. 90 degree angle in both cases. And the symbol for a perpendicular or 90 degree angle is not a curved arc like I drew here, but it is kind of a square. And we say, one of the ways we say perpendicular is to say that the angle is square, right? And so it's a perpendicular angle. And we need to distinguish between conjectures, postulates, and theorems. And I'm going to just do this orally. A conjecture is a reasonable explanation for what something is going to behave like. Right? Like if I draw two lines that are not parallel, my conjecture is that they will probably intersect at some point. That's a conjecture. It's a reasonable guess about what will happen. A postulate is a rule that we take without proof, right? It's there's another word that means very much the same thing. It's an axiom. We hold these truths to be self-evident that all men are created equal. That's from our Declaration of Independence. That is a postulate or an axiom. We hold it without proof. We don't prove it. We simply take this as truth, right? Some things, just like I mentioned before, need to be taken as true, because you can't build a system of logic without having some assumptions somewhere. All right? And then theorems. Theorems are ideas, conjectures that have been proven to be true based on postulates, right? So building on these postulates, we build a whole system of logic by which we can prove certain things to be true. And we're going to be doing proofs in this class. That said, we need to define, have our four undefined definitions, undefined terms. They are point, which we've already talked about, no depth, no width, no height. Line, and I'm just going to sketch a line that continues in both directions forever. Point, line. Okay, I lost my place here. Point, line, plane. Now we draw a plane as kind of a parallelogram, but a plane actually is a flat surface. We don't define a plane, but we simply understand its concept. It is a flat surface that continues forever in all directions, left, right, north, south, east, and west, if you can think of it like that. right? It goes forever in all directions. It is literally a flat surface, a flat sheet of paper. We think in this country of the middle states of the country as being the Great Plains, and that's because a plane is an expansive flat surface. Technically, a plane has no limit. Just like a line, it goes forever in both directions. A plane goes forever in all directions. And then space. Space is difficult to draw, but we can draw it as a cube, right, or a rectangular prism. And we typically draw hidden lines with dots. But just like a cube is bounded, space is unbounded. It has no walls. It just continues forever in 3 directions. Front, back, left, right, up, and down, right? And so these are our 4 undefined notions. And then finally, we have Euclid's 5 postulates. Euclid's 5 postulates. Euclid's postulate number 1. A straight line segment may be drawn between any 2 points. So if I have 2 points, A and B, I can draw a line segment between them. And I can draw just one line segment between them. Okay? Because we have the notion that lines must be straight. So postulate number 1, I can draw a line segment between them. And actually I will add the caveat that without Euclid's 5th postulate, lines could be curved, and theoretically there can be multiple lines through 2 points. That's an area of study for something called non-Euclidean geometry, which is outside the scope of this course. Okay, but just take postulate number 1 as if you draw 2 points, you can draw a segment between them. Euclid's 2nd postulate, a straight line segment may be extended infinitely in either direction. So I can extend line segment AB in either direction. I can extend it to the left and to the right, infinitely in either direction. Okay, and so I can extend it infinitely in any direction. And then a segment can be used to draw a circle where, this is postulate number 3, a segment can be used to draw a circle with one endpoint as the center of the circle and the other endpoint as serving as the radius of the circle. So if I put my compass point on B and my pencil on A, I'm going to draw a circle with center B and with center B and with radius equal to the distance between A and B. Notice how we use that concept of distance again. Okay, all right, so there's a circle going through the center B, but that has a radius equal to the distance of AB. And then all right angles are congruent. That is, if I draw a right angle, 2 perpendicular lines, so we have a line, call it L, and a point on the line, and I construct a line perpendicular to that using my compass here, using the construction technique that we haven't taught you yet. I'm going to construct a line perpendicular to line L, Okay, so we have 2 perpendicular lines. Can't pick up my ruler here. All right. Okay, here we go. Then all perpendicular angles are congruent. So this angle is congruent to this angle. This angle is congruent to this angle. All 4 angles are congruent. And congruent is another notion that they are the same measure. They're the same size. In fact, if I do this construction again over here, And we're going to get into Euclid's fifth postulate, and we're going to determine that if I have two perpendicular lines, two lines perpendicular to the same line, that they will do something unique if the lines are less than perpendicular. Okay, so here we go. Whoops, wrong place. There we go. Right on. Get rid of that. Okay, and so Euclid's fifth postulate says this: if two lines are less than perpendicular, so this angle and this angle together make less than a perpendicular angle. That is, if this angle is 90 and this angle is 90, but I make one of them or both of them less than 90, then what's going to happen, let me draw it something less than 90 here, something less than 90. What's going to happen is if I extend this line and this line out in that direction all the way out here, somewhere they're going to intersect. They're going to intersect. They're going to intersect, in fact, on the side at which the measure of the angles is less than the sum of two 90-degree angles.